All right, hope all of you are doing well. So remind your test for today. Okay. You know the drill, so let me note. So it covers everything up to section 4.4. All right, before we start, we finished chapter 4 yesterday, so I'm kind of don't have anything to write here about what we're going to do today. So do you have any questions about anything for today's test? All of you are in a good place. All right, let's start chapter 5. Little bit, I mean, linear algebra is supposed to be a theoretical subject, and all the theory that you need in some way or the other has been kind of dumped into this chapter. So it might be a little different for a lot of you who have not seen a lot of abstract math. Okay. But I'll try to make it not so abstract, at least for, because it's an engineering course. Okay. So this is about abstract or general vector spaces. So today's lecture, I'm just going to cover and get rid of all the basic definitions and some abstract concepts, which it's good to know, okay, but for the purpose of this course, we probably may not be directly applying those things because it's mostly an applied course here. Okay. So I'll classify today's lecture into two parts, one which is just optional, okay, and the second part, which will be the beginning of the non-optional part, which we will continue next week. So the optional part starts off with the discussion of vectors. Okay. I don't know if you have taken calculus 3 so far, or maybe you have taken physics. When you talk about vectors in general, to most of you, this is what you might think about. Okay. That's some arrow that goes from one point to another. This is R2, which is your XY plane. So all of you know it is something which has got a magnitude or a length, and it's got some direction. Okay. Could also be an R3 where you have an XYZ. So this is the XY axis. For your typical three-dimensional space. So if you talk about something that is hanging in the air, okay, always point the vector to that one from where I stand, and that has got 3 coordinates now. So this is your XYZ three-dimensional space, also called R3. So all these things are vectors which we denote either by some kind of lowercase letters with an arrow. Okay. So these are vectors, and if it goes R2, it will have 2 components. And if it is an R3, it will have 3 components. But you could just keep on extending this. Okay. Our ability to draw things kind of gets limited at this point. We cannot draw anything beyond 3 dimensions, but you can just keep on extending this to something in n dimensions. That's 2 dimensions here. That's the easiest thing to draw. Okay. This is 3D, which is what we see around us. But you could keep on extending it to n dimensions and get a vector with n of these components. Okay. In fact, when you do a problem with, say, 5 variables, you are constructing a vector with 5 components. So it's not something that is completely unknown. We don't just use the word vector there. Okay. So when you're doing a problem with the 6 equations and 7 variables, the unknowns here, x1, x2, x3, x4, x5, x6, x7, that's a vector in R7. And nobody really bothers about drawing that thing. That's not possible. Okay. So there is no clear geometric picture that you can imagine for a situation like this, but it's actually a vector because it has got some kind of a position in the 7-dimensional, whatever that is. So that is what section 5.1 defines. So it defines a vector in an n-dimensional context. Okay. So it's got n components. Again, continuing with the optional part, section 5.2. So what linear algebra would do is take this concept of vectors and then look at what else we could do in math that will have the same properties. Okay. So a set of now I'm going to put that in quotes. Okay. Set of vectors is called a vector space. If the following properties are true. I should warn you that most of these properties are intuitive, but then mathematics requires a fixed set of rules for things to work. Okay. That is why we are confident about math will work all the time, because these things are well set. Okay. So if the following properties are true. And before I write the properties, let me just warn you that the word space here, that is just a mathematician's way of confusing things. Okay. This means a collection or a set. So it's not like a physical space you're talking about. Okay. So it's sometimes that confuses students, is it a circle or a square? No, it's just a collection of things. All right, the properties are the following. So let's take a couple of vectors, say uv in general, okay, and let k be a scalar. So u and v are two vectors, k is a scalar. Okay. Property 1 is that u plus v is also in the same set. And just to save some writing, let's call this set as capital V. Okay, V for vector space. So u plus v is also in the same set V. That's not surprising. You said take two vectors, add them, you get the third vector. Okay. Big deal, right? Property 2, the product k times u is also in V. You expect this in numbers, right? You add two numbers, you get a number. You multiply a number with another number, you get another number. Okay. So this is called closed under addition. Which means that you're not going outside of that set. Okay. You add two numbers, you don't get a different creature, you get the same number or similar kind of number. And this is closed under scalar multiplication. These are the two properties that we will come back to later. Okay. The rest of the properties I'm going to write, it's what I said is pretty intuitive. So property 3, u plus v is equal to v plus u. What do you call that property? Which goes the same both ways. Go from home to work, work to home. What's that property? Give you a hint there. Home to work, work to home. There are those commuter trains out there. Commutative property. So addition of vectors is commutative. Okay. So add two matrices A plus B, B plus A is all the same. Okay. Property 4. If you have a third vector W, U plus V plus W equal to U plus V plus W. What is the name of this property? you can rearrange the parentheses of addition as you like. What do you call this? You have seen this in lower school, I'm pretty sure. Associative property. Okay. We always take these things for granted because we do this in everyday calculations. Nobody cares. Okay, but these are all well set properties. Number 5. Or now that might probably be the biggest thing you ever seen today, right? U plus 0 equal to u, or if you add u to the opposite of u, you get the 0 vector. Okay. What does this property tell you? That there is a what? What do you call this thing? You forgot all these things from your school. That's called the additive inverse, right? So the existence of additive inverse. It also establishes a identity element of addition here for the vector. Okay. Identity element for addition, it's a 0 vector. Okay. There is also an identity element for multiplication, the number 1. So property 6, u times 1 equal to u. It's called the existence of the identity element of multiplication. All of you look surprised that that is true. Okay. 7. If you take that scalar k and do u plus v, like this, you can distribute the k inside, okay, k times u plus k times v, so distributive property of scalars. And similarly, if you have two scalars, say k plus r times u, that's equal to k times u plus r times u. So the distributive property works for one scalar, two vectors, or two scalars and one vector. Number 9, if you have k times r times u, that's equal to k times r times u. People spend a lot of time in really proving these things rigorously and making sure that these are always true. So we have to kind of take back a few steps and appreciate that this is what makes math usable in real life. Okay. Without this, we wouldn't be using math just like, oh, we just do calculations. But all these properties are there because math works. So in other words, we don't get up in the morning and worry about math. Well, is it going to work today or not? Right? That's because all these properties are well set and ready to go. Okay. So, but as I said, the first two are the ones that we will be mostly be concerned about. So properties uh, 3 to 9 are mostly intuitive. Which means at this point, it's mostly a matter of common sense. Okay. Now, pay attention to what we are going to do next. Okay, we are still in the optional material, but the reason why I put those that were vectors in quotes is because from now on, we can use the word vector for a lot of other mathematical objects. Okay. So even if you don't become a theoretical mathematician, it's nice to know what exactly forms the foundation for linear algebra. Okay. So I'm going to write a few examples of what typically would classify as a vector space, okay, which means all these properties are true for the following situations, examples of vector spaces. First one is the obvious one, Rn. Okay. So you take a vector in R2 or R3, all these properties are true. Because there's nothing surprising there. You have probably done it in math, calculus 2 or calculus 3 or physics. Okay. So Rn is a vector space. So that means take any of those things, it's always true. Now you need to pay attention. The set of all m by n matrices is a vector space. See how that word vector is now kind of creeping into other things. Okay, you would never imagine a matrix as a vector because matrix is a collection of numbers. You wouldn't think about a matrix having a direction as such, right? When you say the set of all m by n matrices is a vector space, that means you add two matrices, you get another matrix of the same size. Okay? You multiply a scalar with a matrix, you get a matrix of the same size. And all these properties are true there. Multiply this one would be the identity matrix for that particular situation. Okay. So the identity of addition would be the zero matrix. Because you add a matrix of m by n size to a zero matrix, you get the same m by n matrix. Similarly, the identity of multiplication is the identity matrix. So a set of all m by n matrices without any other restrictions is always a vector space. Okay. So the word vector stands for the matrix there in that context. That is where the abstraction comes in. So that's why it's called an abstract vector space. Now you've been dealing with these things called functions all your mathematical life. Okay. The set of all functions also forms a vector space. See how linear algebra is slowly getting into other things of math. Okay. So example 3, if we take two functions f and g, if you add those two functions, you get another function. Multiply it with a scalar, you get a scalar multiple of that function. Okay, it's commutative, associative, all those properties are true. So this also, the set of all functions form a vector space. So if you add two polynomials, you get another polynomial. Okay. Now, how is this useful for the course that we're taking now? So for example, if you take a differential equation of this kind, ay double prime plus by prime plus cy equal to 0, the homogeneous equation. Okay. You know there are two solutions to this. YH will have y1 of x and y2 of x as the two linearly independent functions. Okay. And you know the principle of superposition. If you add them using any scalar multiple, that's always a solution. Okay. C1y1 plus C2y2 is the solution. I've used that a million times in this course, right? Once again, the idea here is that the set of all solutions form a vector space in this case, because it doesn't matter which way you write this, okay, or if you change the C1 to some other number, C2 to some other number, okay. So the set of all solutions here form a vector space. So from today, at least when you take a linear algebra course, you don't expect a vector to always stand with an arrow at the top, okay? Because it could be any of these creatures here. It could be a matrix, it could be a function, it could be a solution. All these are potential vectors in linear algebra. So it takes some time to get used to it if you have never seen it, and that's okay. That's why I keep this part of the course as optional. I don't expect you to prove anything rigorous or abstract in this course. So section 5.2 homework is highly optional. So please don't spoil your weekend looking at it. Okay, but I'll just do one example just to show you, or two examples just to show you what to expect in this. Okay. So this is section 5.2, problem number 3. Just got multiple parts. I'll just choose 2 of these. Okay. The set of all polynomials of degree equal to 2. Set of all polynomials. You cannot sit here and write all those polynomials. It's an infinite set. Okay. Is this a vector space? Which means that all these conditions always true. I wrote the 9 conditions up there. Okay. Or does one of them fail in some freakish condition? So the critical question you want to ask is, if you add 2 polynomials of degree equal to 2, do you always get a polynomial of degree equal to 2? Add 2 polynomials of degree equal to 2, okay, which means it's a quadratic polynomial. Are we guaranteed to have a polynomial of degree exactly equal to 2? Can you just think about it and give me an answer? You don't have to get stressed out or anything. I told you it's optional, so just let your imagination go wild and tell me what you think. Is it a yes or a no? And if the answer is no, why is it no? So that's a hint. It's okay to say an answer and be wrong. Okay, that's not an offensive thing to happen. You're not being ridiculed by anyone. Am I not recording this? What do you think? Can you give me 2 polynomials of degree 2? If you add them together, will not be a polynomial of degree 2. I can write one of them. Okay, so P1 of x equal to 3x squared plus 5x plus 7. Can you write a P2 of x so that when you add these two, it does not give me a polynomial of degree? Yeah. Now you say it, right? Negative 3x squared. I don't care what these are, plus 8x plus 17. The whole idea is that we were able to get rid of the requirement, okay, that the degree of the polynomial was equal to 2. So P1 plus P2 is of degree 1 now. Okay. which means that it is not a vector space because you went outside of the set when you added the two together. So this is problem 3, part, let's see, part G. Okay. But if you look at 3F, it looks very similar, but that is 3G. 3F, it says that the set of polynomials of degree less than or equal to 2. Okay. Now the condition is relaxed. Okay. I'm not insisting that the polynomial should have a degree equal to 2. It could be degree 1, degree 0. Okay. What do you think the answer is? Is it a vector space now? No, anything could be there now, right? So yes. Okay. Now the answer is yes. So the more strict or the more intense the conditions are, okay, the chances of that being a vector space fails. But this one being less than or equal to 2, which means that is okay, right? This is a vector space. Right. What do you think about this one? This is the one I planned to do earlier. 3I. The solution to the differential equation y double prime plus y equal to sin x. Remember that that is a homogeneous equation. Okay, that is the key thing. So this one is not. A set of solutions to the differential equation y double prime plus y equal to sin x, and it gives a hint. Okay, you do not have to solve this. You don't have to go back to chapter 2 and start, all that process. Okay. All you have to keep in mind was that if you remember this, your y was yh plus yp. What do you think would be the issue here? Yes. So this yp, okay, I think this is what you're referring to, right? This would have been a sin x plus b sin x. There's a reason why it's called a particular solution. Okay, that's pretty locked in coefficient there. You cannot, there is no wiggle room there. Okay, whatever you get out of this one, that is fixed. You cannot take a scalar multiple of that and make it a solution. Okay. This one is okay. The YH, the C1 and C2 were arbitrary. You could take any values of that, it will be true. For YP, there's exactly one value that made it true. Okay. So there is no alternate solution here. That is why it's called the particular solution. Okay. That's unique, which means that if you just add two particular solutions, that is not a solution. Okay. So if we take yp and take a scalar multiple of yp, okay, this is not a solution for the differential equation. In other words, the set of solutions to this is not a vector space. Okay. Now, I haven't posted the solutions to homework from 5.2, just to remind you that it's an optional section. So I would like to leave it that way. Okay, so I won't post the solutions. If you want to go over any of the questions, just come to my office hours and I'll talk about it. So that is what section 5.2 is about. So I'm just sweeping through some sections quickly today. It's time, right? Like, okay, stop. Okay, let me stop there. We'll start 5.3 on Monday. So again, 5.3, the first 10% is optional. After that, we start the more serious material. Okay, so do the test today and then relax over the weekend. Just finish off the determinants and all that stuff. Okay, and that'll be it for today. Okay.
Thank you.
All right.
Thank you.
Take it easy. Don't forget about test number 4. Okay.
Thank you.
Thank you.
Thank you.